All right, so in this video, we'll be doing a quick example of a Newton's universal law of gravitation problem. So the example problem reads, what is the force of gravity acting between the Earth, which has a mass of 5.97 times 10 to the 24 kilograms, and the Moon, which has a mass of 7.35 times 10 to the 22 kilograms, if their average distance apart is 3.84 times 10 to the 8 meters? Now, there's a few things to note about this problem that immediately tell us that we're probably working with a Newton's universal law of gravitation problem. The biggest hint being that we were given two bodies, the Earth and the Moon in this case, and we were told the average distance between them. There is no other formula in dynamics that requires that information besides Newton's universal law of gravitation, at least none that we go over in this class. So, this should immediately point us in the direction of which formula we should be using. Additionally, we do want to take note of the fact that we are in correct units. And mass in physics should always be measured in kilograms. Both of our masses are given to us in kilograms, so that's all good. And distance should always be given to us in meters, which in this case it is. So again, we are all good. Now, to actually work through this problem, we need to, one, understand the formula that we're working with, and then two, understand what in the formula we're actually trying to solve for. So, if I could just bring up the TV real quick, like so, I can start to walk you through that process. So, camera should start tracking me now. Perfect. All right. So, in order to do this, we're going to be using this formula right here, Newton's universal law of gravitation. Now, this formula states that the force of gravity, F sub g, is equal to our g, big G, Newton's universal law of gravitational constant, which is at 6.67 times 10 to the negative 11. Now, this is why we went over how to do scientific notation again, because we have that number that's really, really small in this equation. It is worth noting here that we are ignoring what units this is in. So long as we understand that everything in this formula either has to go in with proper units or comes out with proper units. As far as we're concerned, this number is magic. Okay, and it makes everything come out correctly without us having to worry about why it's happening. Okay. Yes, we could talk about the exact science and math in terms of why all those units are correct, but quite frankly, I don't want to do that, and I doubt that you want to listen to that. So, what we're going to do instead is we're going to make our list of variables. So, for our list of variables, we're going to have 5 different variables here. Okay, we're going to have f sub g, we're going to have g, m1, m2, and d. So, let's get to work here. Okay, we know for a fact that our unknown in this case is f sub g. And we know that because the problem explicitly states that the force of gravity is what we're looking for. Okay? The question literally reads, what is the force of gravity acting between the Earth and the Moon? So f sub g is unknown. Big question mark right there. But we do know what units it should come out to be. We know for a fact it should come out to be newtons because it is a force, and force should always be coming out in newtons. Now, G is always going to be that 6.67 times 10 to the negative 11 number. Okay? It will always, 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 always be that number. Never any other number. Okay? We do not use capital G for anything else in physics. So, let's move on to our masses. Now, M1 and M2. It doesn't necessarily matter which one is M1, which one is M2, so long as they're different, and so long as you remain consistent as to which one is which. For me, I'm going to use M1 is the Earth, M2 is the Moon. But you will get the exact same answer if you decided to use M1 as the Moon and M2 as the Earth. It doesn't really change anything. So, M1 is 5.97 times 10 to the 24 kilograms. So 5.97 times 10 to the 24 kilograms. And that is given to us directly by the problem itself. Okay, so we don't need to worry about that. M2, also given to us directly by the problem itself, it is 7.35 times 10 to the 22 kilograms. Which leaves our last variable, distance. Now, distance we know should be in meters, and if you look at our example problem again, you may need to rewind at this point to double check it because it was a bit of a long problem. But it comes out to be 3.84 times 10 to the 8 meters. And we can tell that that's a distance because it is in meters. Okay, we can always use our units to double check what these units are supposed to be in. Okay, what these variables are representing. Okay, because those units should never ever change. If they do change, we have to do conversions. So that leaves us in a position where we can actually start plugging into our formula and solving. So in order to do that, I'm going to stop the tracking. Okay, that should work. Perfect. So at this point, we can actually see on the side over there the various equations the various numbers that we have available to us. And all we're going to do is we're going to plug them into Newton's universal law of gravitation, which is just off a frame here, but hopefully you have written down at this point. So F sub g is our unknown. That is what we're solving for. Is equal to g, 6.67 times 10 to the negative 11. I'm going to use parentheses here just to make sure it's very clear that these are three separate numbers. M1 is 5.97 times 10 to the 24. And finally, M2 is 7.35 times 10 to the 22. All of that, okay, I know it looks like a lot. I promise it's not that bad. But all of that is going to be divided by our distance, 3.84 times 10 to the 8. Squared. Okay, so it is that number squared. Now, at this point, this looks like a lot. Okay, there's a lot of numbers written on the board. It can be kind of overwhelming your first time looking at it. But what you end up going to find is that it's actually not that bad. Because if you have the right calculator available to you, all of these numbers are no more complex than a 1 or a 2 or a 10 if you use the right notation. So let's go ahead and go through how to do that. So all I'm going to do right now is I'm going to simplify this a little bit. Okay, I have three numbers being multiplied up here. I can simplify that into one number by just multiplying all three together. And I have a number being squared down here. I can simplify that by just doing that square. So in my calculator, I'm going to pretty clearly and explicitly say what I'm doing here. Mind you, I'm using a TI 84 plus CE. This general notation should work for any TI calculator. I do not know exactly what it would be for a non-TI calculator. And for some reason, it started tracking me again. So we're just going to make sure that stops. Perfect. Okay. Still learning how to use the technology here, as you can tell. So in my calculator, I'm going to do 6.67. And then I'm going to hit my second key. For me, that is at the very top left. It's a bright blue key. And what that allows me to do is it allows me to use my second functions. Okay, these are alternative functions that my calculator can perform by pressing these buttons, but that are not listed on the button themselves. They're usually listed in blue ink above the button. So I'm going to find where it says in blue, EE. Okay, it'll look like two capital E's, and it'll be in blue. So it'll look something like this. It'll look something like that. So when I do find them, I'm going to hit that button, and I'm going to put in whatever my exponent is. In this case, that's negative 11. So 6.67 times 10 to the negative 11. So I just hit 6.67 e minus 11. And then I don't need to put any parentheses or anything like that around it. I can just keep on going as if this is a 1 or 2 or any other regular number that I'm used to working with. So continuing on, I'm going to do 5.97, second e, 24, times 7.35, second e, 22. Just like that. And I'm just going to hit enter. And when I do that, I'm going to get a really big number. And that makes sense because I'm multiplying two really big numbers by a smaller number. But ultimately, because I have two really big numbers, I should get an overall bigger result. I get, rounding, 2.93 times 10 to the 37. Okay, that is what all this up here simplifies into. Now, let's do the bottom part. 3.84 times 10 to the 8 squared. So I'm going to do 3.84, second E, again, okay, second EE, nothing crazy here, 8, and then I'm just going to square that as if it's like 2 squared or something like that. I don't need any parentheses, I don't need any of that nonsense. So I do that, and I get, again, a rather large number, which makes sense. I'm squaring a number, it should get bigger, especially if it's more than 1, and this is a considerably larger number than 1. So I get 1.47 times 10 to the 17. From here, my final answer is just going to be this number divided by this number. That's all it will be, plain and simple. So I do that out. 2.93 times 10 to the 37 divided by 1.47 times 10 to the 17. Now, mind you, I'm using the exact values here. So your answer may differ slightly from mine. But my answer comes out to be 1.98 times 10 to the 20 newtons. It is very important that I include that unit. And the reason why I know it's in newtons is because I am solving for a force. Okay? If I'm not solving for a force, it's not going to be in newtons. But because I'm solving for a force, I know for a fact that it must be in newtons. My last thing I'm going to do is I'm going to see if this answer makes sense, logically speaking. And in my opinion, it does. Okay? I'm talking about the Earth and the Moon, two very, very, very large rocks, especially compared to a human scale. It makes sense that I would need a very, very large amount of force to keep the two of those things together. So 1.98 times 10 to the 20 newtons makes sense. If you guys somewhere in the ballpark of this, as long as you're like around 2-ish times 10 to the 20, you probably did everything right, but your rounding may come out a little bit differently than mine because you may not be using the exact same calculator as I am. That's why I personally recommend getting a nicer calculator, especially for things like physics, in general, just STEM math in general. Just because it makes doing these rather specific calculations more exact and more precise. So with that being said, that is how you solve a problem using Newton's universal law of gravitation. I know it looks like a lot, but this is the only type of problem that I will ever make you solve. Okay? You'll always be solving for a force. So with that all in mind, I hope that this video was helpful. If you enjoyed this video, please make sure to leave a like down below. Okay? Make sure you smash that like button. Make sure you hit that subscribe button. Keep an eye out for future uploads. And I will see you all in the next video. Have a good one.